Okay, hello, everybody, and welcome to this special instance of the Physics Club. It's a pleasure to have with us here Monika Aidelsburger. Monika got her PhD from the Ludwig Maximilians University in Munich. She did her postdoc in Paris at the Collège de France with Jean Dalibard, who I'll just mention as an aside will be giving our Rosenthal lecture next week. Maybe, yes, okay, yeah. So Jean Dalibard will be here next week giving our Rosenthal lecture. Monika, in 2017, joined the faculty back at Ludwig Maximilians Institute, where she is currently a professor and a W2 research group leader at the Max Planck Institute in Garching. Her group does world-leading experiments using ultra-cold atoms as simulators of topological and non-equilibrium quantum many-body systems. And we're looking forward to your talk. Thank you.
Thank you so much for this kind introduction. Also thanking everybody for coming to this special slot that I told the students just a few minutes ago. I shifted because of teaching, not knowing that Tuesday was a free day for the students, and I still missed my first class that happens just now. So anyway, thank you so much for that. Yes, so I will be telling you some of our experiments that we are doing on quantum simulation. And first, I would like to spend a little bit on introducing the platform and what we can do, what observables we have, and then focus on this one main example of topology and how we can do quantum simulation of topological phases of matter. So let me get started. So I would like to zoom out a little bit before I get into the details of our experimental platform to motivate a little bit why I believe that quantum simulation in this analog fashion is very useful, especially with the capabilities that we have right now. And so there are all of these applications out there that we are all excited about and hope that we can build with our quantum devices. They have a broad range of applications, at least we hope that some of them will manifest that range from material science, quantum communication, building efficient quantum computers. And what I would like to emphasize is that I think the new key ingredient that we are trying to make use of is interactions between many particles. So we already have all these beautiful experiments where people can control single ions, single qubits, photons, and so on. And now we are really trying to make use of all the control capabilities that we have available and put many of them together and engineer the interactions between them in a way that we can generate useful entangled states that are a resource for applications. Okay, so why do I emphasize that? I think that's really the new ingredient, finding these useful states and then engineering them and making them work for applications. And this is sort of what we are all excited about, because there's this computational complexity. We know that the Hilbert space scales exponentially with the number of particles that we put together. And that's what we want to make use of, but that's also the challenge to begin with, because we also have to manage this huge space. So we have to not only manage it in the lab, we also have to understand it, because if we don't understand it, we also don't know what applications to come up with. Okay, and so this is basically what we're excited about, but also what makes it hard for us to build devices. And in order to overcome this challenge, you can build quantum simulators in the lab. You can pick certain problems that you're interested in. I will give you an example of condensed matter inspired model systems. And then you can put your system together in the lab, you know, the microscopic processes, the microscopic interaction terms in your system, and then you can learn from it. You can ask questions and then generalize from there. And this is the idea of quantum simulation, and there are many different platforms that you can use in order to do that. This is a very small selection. You also see a couple of names. There are too many groups out there, so I will not be able to give you a full list of references. So I just selected a few pretty pictures. Superconducting qubits, ion traps, Rydberg atom arrays, and neutral atoms. Here, this is a picture from our lab that I've taken from our cesium quantum gas microscope. And immediately also from this list, what you see is that people working on developing digital quantum computation devices in order to have a universal quantum computer also do analog quantum simulation experiments. The same ingredients, the same platforms. Is it qubit degrees of freedom in a transmon or photonic degrees of freedom? You can build them up together in a way that you can do both. You can try to do a universal quantum computing device or an analog device. So I will be focusing on this one and give you a specific example and also tell you a little bit more about how this platform works. So what you see here is a square optical lattice where we trap individual cesium atoms. So we have built a microscope that I will show in a second, such that we can resolve the distance between two neighboring atoms. In this case, that's 767 nanometer. And then each one of these bright blobs corresponds to one cesium atom. Okay, so this is the typical length scale. So in the standard square optical lattice, what we can do is we generate an AC stark shift, a potential energy landscape, by counter-propagating laser beams. It goes in one direction, straight to reflected. This gives you a periodic structure of intensity peaks and nodes, and then the atom will see this as a periodic energy landscape. And the distance is then naturally given by the laser wavelength that you use to generate this interference pattern. And so that's the simplest configuration. In principle, you could cook up any interference pattern you like. I heard about quasi-crystals today, so you can really do any optical potential landscape that you want. But it's challenging, as you can see, because resolving and controlling individual atoms requires high resolution imaging systems, because the distance is on the order of 0.5 micron. That's really, really close. And why is it important for us? Well, because we are building analog quantum simulation devices, meaning the dynamics of the atoms in this Hamiltonian is given by two main parameters: J, the kinetic energy, which is the hopping matrix elements between neighboring sites, and U, the Hubbard on-site interaction energy. So what happens is that these two wells are so close together that this barrier is large, but not large enough to prevent any motion in the lattice. So there's actually a significant tunneling amplitude between neighboring sites, so that we can study this competition between kinetic energy and interaction energy. So that's really one of the paradigmatic condensed matter model Hamiltonians that you can study in order to do strongly correlated physics in your quantum simulation device. So that's what you get naturally if you load a cold sample of neutral atoms into this periodic potential. And then you can try to develop novel techniques in order to make this Hamiltonian more complicated. I will say more about having topological phases of matter, but you can also find other ways to have more long-range interactions. This is just on-site, have magnetic interaction terms. So there are a lot of different ways in order to make this model more complicated. Here, I'm also focusing on bosons, but we can also work with different isotopes. So we have fermions. So it's a large playground that is available. So how do we take these images? This is a schematic view of our microscope. The glass cell, in our case, is fully made of glass. Sorry, the science chamber is fully made of glass. It's actually quite tiny. So what you see here, from top to bottom, that's just 1 centimeter, and the top window has like a diameter of 3 centimeters. It's a very tiny glass cell where we trap our sample. We have a square optical lattice in plane, and then out of plane, we confine them in an additional vertical lattice. And now, after doing a quantum simulation experiment, which I say a little bit more about this in a second, in order to generate these images, we freeze all the dynamics. So we have our quantum many-body system. Then we suddenly ramp up the potential so that the atoms cannot move around anymore. And then we shine in near resonant laser beams, as shown by these light red arrows, in order to scatter many, many photons. And there we have to keep a balance of scattering, which heats up the atoms, and cooling at the same time. So these are usually arranged in a molasses Doppler cooling type geometry. And then we scatter a few thousand photons in this case to collect these snapshots. And what this gives you, let me show you, is actually a projection of your many-body wave function onto one specific configurational basis. So if you write down your quantum many-body wave function, you have a superposition of all these different configurations of atoms in your lattice. And taking a picture projects you onto one of them. Now that immediately tells you that in order to extract anything useful about your quantum many-body wave function from this picture, means you have to sample. You need to take many of them, and then you can evaluate different types of quantities. And this is also what the first part of my talk will be about: what observables can we extract from these images? Is there a question? I'm not sure. Yeah.
Sure, but this picture doesn't have it's a real quantity, right? So it doesn't have a face.
That's right. Yes. So what you get, for instance, if you now sample many of them, would be the probability. I could analyze the probability of finding this configuration when sampling many of them. And there's no phase information whatsoever at this point. And I will tell you one trick on how you can extract some phase information. Not full state tomography, but some phase information from these images. Yeah.
Relation to this question about the phase, are these are not involved, say, or they?
Yes, in the configuration basis. So they're in the Hamiltonian, they're coupled, but this is the Fock basis. So yes, it's just configuration. So then you can evaluate also mean quantities like mean density, but there's also interesting information in the fluctuations or the correlations. You can evaluate density correlation functions from these images. So in principle, there's a lot of information in there. But exactly what I wanted to get at, there's also a lot of information that you miss. For instance, relative phases. If you want to know something about coherences in the system, you cannot easily get that. But let's first, let me show you one more image on the next slide, which is about what system sizes we can actually achieve. And I wanted to mention that because a lot of the technological development of the machine that we have been doing was to make large, nice, homogeneous systems. Why do I emphasize that? Because I told you that these periodic potentials are generated by interfering laser beams, right? So I have like 2 counterpropagating laser beams that confines my atoms in this periodic potential, but I also have a Gaussian envelope, and that generates a harmonic trap that keeps my cloud in place. If I want to do a quantum simulation and really learn something about the system, I would like to have a very clean one. I don't want to have to deal with this harmonic trap, which complicates analyzing a phase diagram and things like that. So I really want to make it flat, nice, and homogeneous. And already from the way that I'm doing my hand gestures, you can imagine that what I actually want is a box. I don't want to have a harmonic trap. And that's exactly what we did. Because if you look at the setup, there's this high NA imaging objective underneath, which I use in order to take the images from the atoms in the first place. But I can use it in reverse. I can now project potentials into the atomic plane. So what we do is we project repulsive walls into the atomic plane that keeps the atoms in place and makes a nice flat bottom trap. And then you get images like this. So here you see like a box Mott insulator. This is how we call it. It's generated by ramping across a superfluid to Mott insulator transition. And now every side is occupied by one atom. It's not perfect. There's entropy, finite entropy. So we have 98% filling in this system. It's very large. It has about 50 by 50 lattice sites. And this is a typical system size that we like to work with when we simulate 2D systems. Now, you're probably a little bit puzzled by this picture because you don't see the individual atoms anymore. And this is because I cheated a little bit on the previous picture. Our energy scales, so our lattice constant is actually very, very tiny. It's only 380 nanometer because we want to have very large kinetic energy or tunneling terms. And 380 nanometer optically is extremely hard to resolve. And so I showed you a nicer picture where I increased the lattice constant by a factor of 2 so that you believe me that we can see individual atoms. Nonetheless, this is actually a very interesting problem that we have worked on for a while. Because it's quite deterministic. It's an easy problem in principle to solve. If you look at this image, you know the response from each individual atom. It's a point spread function. You can calibrate the location of the grid. You can calibrate the lattice constant. So even if you are working in a regime where the resolution is not good enough, like here, it's still a deterministic deconvolution problem in some sense, which is very hard to solve because there's a lot of noise. It's a finite signal to noise ratio. Anyway, we came up with this unsupervised machine learning algorithm that allows us to reconstruct these images. And it's actually also a very interesting physical system to work with because it's in a sub-wavelength array. And what I mean by that is the lattice constant between 2 neighboring atoms is much smaller than the imaging wavelengths or the wavelengths that the photons have that scatter. So you have light-induced dipole interaction between them. So there's a lot of collective light scattering happening. So we see a lot of super radiant effects in this array that we work with. But it's just on the side. If you're interested, you can look up our paper. It's actually quite nice. And what I like is that this machine learning network, this algorithm, learned that there is super radiance. It really captured all the super radiant phenomena. All right. So let me tell you a little bit more about how to get more information about the system. And to zoom out also a little bit, I want to give you 3 more general goals that I think our community is working on, because by now there's like a ton of different quantum gas microscopes out there, many different atoms, different properties, different Hamiltonians that people look at. And I just want to highlight a few of the things that I think are at the moment relevant in order to push for. One I already mentioned is to extract more information about our system. It also ties in a little bit with verification and benchmarking, because if you look at the simulations that are being performed right now in terms of system size, but also coherence times, they are extremely, extremely good. But we don't have the same framework as, say, digital quantum computing devices, where we know how to deal with our errors, where we can do a benchmarking analysis of the performance of our system. That's much harder in this analog mode. But they're actually extremely good. It's just something to work on, how to verify and benchmark these systems. And then we want to expand the range of applicability. And unfortunately, I didn't put this example now on the slide, but something that we're working on is studying lattice gauge theories. And even though our systems have only realized like very small systems of few particles, because the coherence is so good, we can actually perform very long time simulations. While I looked at the recent result from Quantinuum, they need like millions of snapshots and a few thousand gates, which is very, very difficult to do. So I think there's a lot of potential using these analog quantum simulators, but we have some work to do in order to verify and benchmark their performance a little bit better. Okay, and to do that, we want coherences. We want to be able to do a bit better state tomography, for instance. So let me tell you what the trick is in order to get more information of your state. So if you just freeze the dynamics, we get this configuration basis, local occupations of atoms in the array. Now, I insert an additional step before reading out this state and perform local dynamics. So I think, yeah, you can kind of see it. So we project from the fully connected 2D square lattice onto a lattice of dimers. So now only the two sides that are still connected with a line undergo dynamics. I have not taken an image yet. And the dynamics within each dimer can be understood in this double well representation. And a double well is great because it's like a two-level system. We can put it on a Bloch sphere and understand the dynamics that is happening in this two-level system. Okay, so I label these two sides as left and right and put it on a Bloch sphere. So now what we can do in this dimer is we can control the operations that happen. I can either have a symmetric coupling between them, so that's just my tunnel coupling J. In spin language, that would be a sigma x operation. Or I can apply a tilt between the two neighboring sides, which is nothing but a sigma z operation. And these are, remember, my optical interference patterns. So all I need to do is play with the intensity of my laser beam in the relative phase between two separate wavelengths, and I can control these dynamically. Okay, so great. That means that on this level of individual dimers, we can apply these operations. So we can perform rotations, arbitrary rotations on the Bloch sphere by just combining sigma x and sigma z. So let me walk you through what you see here. So we have left and right on the two poles. So if we perform just a normal density measurement, that would be evaluating the expectation value of sigma z. Or in this double well picture, it's the imbalance between the two sides. But sigma x is kinetic energy. It's like the symmetric coupling between neighboring sides. So in my Hubbard operators, it would be this term. It's just A dagger A between the two sides of the Hamiltonian. And then sigma y, actually in Hubbard language, corresponds to a current operator. So that means if I'm now interested in not measuring occupations, but let's say the currents between neighboring sites in the lattice, I apply a pi/2 rotation before the readout, and then I get a locally resolved map of the current distribution of my state. Or I could also read out kinetic energy, for instance. So this allows me to ask fundamentally different questions, for instance, about energy transport or like anything else, and not just occupations. Okay, so this can be read out in a single shot basis, which means we can also evaluate all the other quantities that I mentioned before, like current correlations or fluctuations in a current operator. So it's everything that we could evaluate on density, we can now do for the other observables as well. And so let me show here a little toy example, like a little toy state tomography experiment that is shown here in this pulsed language. So left means we have now our two-dimensional array, and artificially I prepared it in a way that each dimer has one atom on the left side. I just select this to be my initial state, and then I prepare different states in the Bloch sphere. So I apply a pi/2 rotation and a variable c rotation to prepare different angles of my vector in the equatorial Bloch sphere, in the equatorial plane of the Bloch sphere. And then I read it out using the different basis measurements that I've explained before. And then as I scan the equatorial angle, you see that these different observables, the expectation values oscillate. If I sum them all up, if it's a pure state, they should all be equal to 1 because I've prepared a pure state. So this is just a little toy example of that this actually works. And this is averaged over many thousand double wells in parallel. So this is an operation that we can do very efficiently. And let me just highlight, okay, so it's not perfect due to potential energy, so potential disorder in the 2D lattice. But let me just emphasize that we can also apply this locally. So I told you that we can apply this box potential by projecting light through the objective. That means we can also selectively tilt some of these diamonds. So I can rotate my measurement basis locally. And we have demonstrated this in a little toy experiment. That's the sequence again, all the atoms starting on the left, pi/2 pulse, flip them in the equatorial plane, doing a selective C rotation, and then applying a pi phase shift on every other double well just to demonstrate that this is possible. And why do I find this exciting? It's because now you have access to more complex correlators, not only between density or current, but between sigma x, sigma y, sigma z. You can cook up any complex correlator that you would like to evaluate from your state. And not only that, you can also apply that to prepare different initial states. So usually for our quantum simulation, we place atoms in different locations. We do, for instance, a quench experiment, but it's an initial product state in the configurational basis, in the Fock basis. Now you can apply these local manipulations in order to imprint currents or other properties on your initial state. And so this opens up a whole new area to play with, which puts you in this region of hybrid digital analog devices. So you have your nice coherent analog Hamiltonian evolution, and you can sprinkle in this digital control either for state preparation or readout, which just increases the flexibility of the machine and ties into the question of finding ways to benchmark and verify our quantum simulation devices. Okay, questions on, yeah.
But you also, you still have many atoms, right? And you in fact can rotate, but you rotate all of them, or you can pick which one you rotate, which pair you rotate?
Both, actually. So we can either rotate them all at the same time. This we can do very efficiently just by playing with the interference pattern. And the way to locally apply this rotation is by using this high imaging objective. We project with a DMD, like a digital micromirror device, a potential bump into the atomic plane. And this then locally tilts one of the double wells, which applies a sigma z rotation. So exactly. So you can also just rotate one if you want to. Okay. So after having this toolbox, let me first tell you maybe two broad classes of experiments that we do, and then I will focus on one of them. So the way these experiments work is that first we prepare low entropy gases in a periodic potential, and the Hamiltonian is engineered in the lab by hand, bottom up. So we can control the parameters and we can study phase diagrams. This is what I would call studying ground states. We try to be as cold as possible, lowest entropy as possible, and then we tune parameters. So this picture is a schematic that I've taken from Marcus Greiner's lab in Harvard, where they are looking at the Fermi-Hubbard model and understanding the phase diagram of the Fermi-Hubbard model. This very, very challenging task, trying to get to lower and lower entropies in order to see these physics. But there's something else that is very interesting and that we are also extremely good at, because preparing these low temperature ground states can be extremely challenging depending on the model. But we know where to place particles by hand in the lattice in an initial product state, and then turn on dynamics. This is also something that we can do very well. We know how to engineer the Hamiltonian terms and special initial state configurations. And dynamics is a very, very hard problem theoretically to solve. So this is really, I think, where our platform shines, because this is something that we just know how to do very well. And here you see an example where this I've taken from Emanuel Bloch's group in Garching, where they've looked at localization in 2D in the presence of disorder, trying to address the question if MBL exists in 2 dimensions. And again, to emphasize a little bit, so what we do is really engineer this Hamiltonian H by hand. There's no trotterization or decomposition into gates as in the digital case. We try to engineer this microscopic Hamiltonian, microscopic interactions directly in the lab. And there's a very interesting paper, if you want to learn more about this, on how to think about errors in this case, which again, just go beyond what we know from single and 2-qubit error estimates. For analog Hamiltonians, you need to think a little bit on what that actually means. Okay, so this I will skip. So let me give you one example of systems that we think are interesting for quantum simulation that we would like to study and engineer in the lab. So this is the big topic of topological phases of matter, which I've already worked on for some time. And one of our big motivations is to study fractional quantum Hall physics, which is a very challenging topic to begin with. So let me just remind you about the integer quantum Hall effect. I know there are experts here, so I hope there are a few who don't remember the integer quantum Hall effect. So in a nutshell, what it is about is you have a 2-dimensional electron gas. You can put it in this Hall bar geometry and measure transport properties. So there's an out-of-plane magnetic field sending a current through the sample. You can then measure the longitudinal and the transverse response of the system and extract the longitudinal and transverse Hall resistance, for instance. Now, in the classical case, you find this nice linear behavior. And then in the integer quantum Hall effect, you find that there are plateaus. And what is so beautiful about these plateaus is that they're extremely precise. And the reason for this is rooted in the topology of the energy bands. So in this integer quantum Hall effect, you can understand it in a single particle framework, doing a band structure calculation of your periodic system. And then for each energy band, you can assign an integer number that is given or encoded in the geometric properties of the band. And this integer number shows up in the plateau value of this transverse Hall resistance. So it only depends on natural constants and an integer, the topological invariant, known as the Chern number. Now, if more bands are filled with electrons, you sum them all up, and this gives you the plateau value. And now what you see here in the presence of this plateau is that actually if you change your system a little bit, so there's disorder in the system, you change the parameters, it remains pinned to its integer quantized value. So what we are fascinated by when it comes to topology is the robustness in the electronic properties, which of course immediately makes it interesting for applications. And this is also what has been immediately realized when integer quantum Hall effect has been found, that this is, for instance, a very good way to compare measurements between different labs. It's a very good standard if you have such a system that gives you a very precise measure of resistance, which you can also find now again in the new SI units definition. Anyway, so now if we add interactions to the system, it becomes more complicated. And there are phases that occur due to the interaction between atoms. And why do I emphasize that? Is because theoretically, this is very challenging to treat. It's not that you can start with your non-interacting Hamiltonian and then perturbatively add interactions to your system and try to understand the properties. These are phases of matter that intrinsically due to interactions, strong interactions between particles. And so some of these fractional Hall plateaus, you can find trial wave function and try to understand their properties. But theoretically, it's a very, very hard problem to work on. And these phases also have very interesting properties. There's topological order, there's non-local entanglement, and the excitations have unusual statistics. They are anionic excitations. And so having something like that under the microscope and being able to study this in an analog quantum simulation device would be, of course, amazing. So we could study, change the parameters, try to manipulate these fractional excitations, and maybe eventually even use them for applications. So this is a very interesting area to do quantum simulation experiments. It's also a very hard area to do quantum simulation experiments because it's not something that we can have naturally in the lab. So all the story that I just told you about these 2-dimensional electron gases having a perpendicular magnetic field, doing transport measurements, all this doesn't really naturally fit into what I've shown you, where we have these neutral atoms that are placed in a periodic potential that we make by interfering laser beams. And the problem is that we need some orbital magnetism if we want to replicate some of these physics. And in order to do that, we find, again, a very simple toy model that gives us the main properties. So you have the non-interacting Hubbard-Hamiltonian here, the hopping matrix element between neighboring sites. And now we ask the question, what do we have to do in order to make this topological? And the easiest way to see what we have to do is to write down the Hamiltonian for a charged particle in its periodic potential in the presence of a magnetic field, and then try to replicate it in our synthetic quantum system. So what happens for a charged particle in the presence of a magnetic field is that these hopping matrix elements, they become complex. They're pulse phases, and those are discretized versions of the Aharonov-Bohm effect. So in the Aharonov-Bohm effect, you have a charged particle, and if you make an interferometer, you make it travel around two different trajectories and close a loop, then there's a relative phase at the end of interferometer, at the end of your interferometer that is proportional to the magnetic field piercing the area of your interferometer. So if we do the same calculation for the square lattice, there's a finite phase, a Aharonov-Bohm phase associated with this geometry that is the sum of all the phases associated with the complex tunneling matrix elements. And then this is proportional to the flux piercing the unit cell. So this is like the simplest model that we can implement in order to see these topological phases of matter. And now we can actually forget about the physical system. All we need to do is find a way to make these phases complex. And the way we do this is by periodic driving. So we have a Hamiltonian that we engineer in the lab. We change it periodically as a function of time with period t. And this allows us to engineer a new system according to Floquet's theorem, where the time evolution operator after one period of the drive is now described by this Hamiltonian HF, which is effectively time independent. And the picture that I would like you to have in mind in order to understand why this gives rise to some novel physics is a rotating saddle potential. So you know that if you have a saddle potential, you cannot trap a particle because it would roll away in one of the two directions. But now if you start rotating it, you can effectively create a trapping potential in 2 dimensions. And something similar happens here. So in the limit where the driving frequency is extremely fast, to lowest order, the Hamiltonian is the time average over one period of the drive. So you have this very fast time-dependent control, you average over it, and then effectively you get a new Hamiltonian describing the system that you have in the lab. And specifically in our case, the game that we play is always kind of the same. So we have a 2-dimensional square lattice. We want to modify the motion of the particle in that lattice. So first we inhibit it. We apply a potential energy difference to pin them. They don't move at all. And then we shine in laser beams to assist the hopping. It's a resonant modulation at the energy difference between neighboring sites. So the atoms can resonantly absorb energy from the drive, and the phase of this drive is imprinted on the hopping. If there are atomic physicists in the audience, another way to think about this, which is fully equivalent and doesn't require any Floquet language whatsoever, is you have 2 levels. You implement a 2-photon Raman coupling, and the phase of your laser beams, the difference phase of the laser beams is imprinted on your complex Raman coupling. And this phase is your laser-assisted tunneling phase that shows up in the Hamiltonian. It's essentially the same thing. Okay, so now we have that. We do that for our 2-dimensional lattice. And now we can start to do a few little toy experiments to see if that works. And I still like to show one of the first experiments that I did during my PhD, which is now a long time ago. But you can try to see something like cyclotron orbits. So you put one atom on a plaquette. It's just 4 sites. It's highly discretized. And you let it tunnel in one direction. Now, if you just do that without a magnetic field, you see Rabi oscillations. But now you can track it in the presence of a magnetic field. So this is the mean position in the plaquette. And what you see is that it undergoes some type of chiral motion. It looks a little ugly, I know, but you have to remember that it's only 4 sites. And this is now about 15 years ago, so we didn't have a microscope. So it was a very challenging experiment to do, but you see this kind of chiral orbit emerge. So by now, and it's a slightly different technique, but this is from 2020, you see very beautiful cyclotron orbits. It's an internal state basis, but it's essentially the same technique where you see that nicely people replicate cyclotron motion in a synthetic quantum system. And because now we do have a microscope, we can generate a map of currents. So here I told you, in order to reproduce this measurement, we put one particle on 4 sides. Now what I can do is prepare ground state in such a plaquette. And this gives you chiral currents, like tiny little chiral currents in plaquettes. And in order to benchmark our current measurement observable, you can now generate a map. And so this is an actual measurement that we took in the lab. We're now on, like, each one of these 4 dots is actually connected. So here's a zoomed in version. We prepare the ground state. We put in each one of these plaquettes exactly 2 particles. They interact. We prepare them in the ground state, and then this shows this chiral currents, which are displayed by this arrows. And here's a full site-resolved map of this current distribution that we have taken in the lab. And you can see that some of these plaquettes, they look a little bit broken, but it's actually just because of the shot noise. It's just because of the finite sampling statistics that we took in the lab. So now we have this nice microscope that can do topological physics and generate local maps of occupations and also current distributions in the system. Okay, so this is 2 interacting plaquettes, 2 interacting particles on a plaquette. So I started this whole story telling you about fractional quantum Hall physics. So, okay, we are not quite there. So let me tell you a little bit about the state of the art and what people have been doing in this regard. Okay, so what about many-body? And we have been trying to push our experiment to do exactly that and engineer topological phases of matter with many particles. So let me first tell you what's the state of the art. So this is an experiment, again, from Markus Greiner's lab in Harvard, where they have put 2 particles and engineered a Laughlin type fractional quantum Hall state. The smallest version that you can think of. So it's a lattice of 4 by 4 sites, and using 2 particles to prepare the ground state. Again, also in a microscope. There are alternative ways to engineer these fractional quantum Hall type systems by making use of rotations. So here the idea is that, similar to just imprinting phases by hand, now you make use of the equivalence between a Coriolis force and the Lorentz force, which just mathematically look the same, in order to engineer a Laughlin state. And here this has been done, again, with 2 interacting fermions in order to engineer a Laughlin wave function. And then there are also realizations with photons and cavities and superconducting qubits. But this is really what people have managed to do so far, 2 interacting particles and trying to get as close to a fractional quantum Hall wave function as possible. So why is it so hard? Like, there are all these beautiful techniques that we have worked out since 15 years in engineering topological band structures. There are a lot of techniques on studying the geometric properties. We have performed Hall measurements. We have performed measurements of Chern numbers, all in the non-interacting regime. So what's the problem? And this brings us back to the discussion of the periodically driven Hamiltonian. So we have this periodically driven Hamiltonian, which we describe with a time evolution operator after 1 period of the drive. But this comes at a cost, meaning if I write down the wave function that solves my time-dependent Schrödinger equation, there's a periodicity in energy space. So the energy shows up as a phase, and it's only defined up to integer multiples of the driving energy quantum h bar omega. So similar to Bloch's theorem, where you have your periodic crystalline space, and you write on your Bloch wave ansatz to solve your problem, and you have a quasi-momentum as a good quantum number. You can plot this in a reduced zone scheme or in an extended zone scheme. Same now happens here with my quasi-energy space, which I've plotted here in the extended zone scheme. So here, this is an example where I use the periodic driving technique in order to engineer a cosine dispersion. Okay, I could do that. And now I have infinitely many copies separated by h bar omega. So this is the non-interacting answer to the problem. If I now put 2 particles at the bottom of the band, here this is quasi-momentum, q equal to 0, they would be stable. I could put interactions into the system, but the system would be stable. Now, if I think about adding to this non-interacting band structure interactions perturbatively, I get new scattering resonances between them. And now intuitively, if I just think about what scattering resonances can happen if I conserve energy and momentum, then these two particles can collide and they can redistribute energy. One could go down here and one could go up here. This conserves energy and quasi-momentum. But if I now plot it in the reduced Brillouin zone, it means that two particles that were initially at q equal to 0 acquire finite quasi-momenta plus and minus k. So this is what we then call heating in the system. So this is just saying that if I have my periodically driven system, due to the fact that I do not conserve energy anymore, it's only conserved up to integer multiples of the driving energy quantum, I can redistribute my energy, and that increases the energy or temperature of my particles in the band or in the system that I was trying to engineer in the first place. And this can actually be quantitatively defined. If this is the Hamiltonian of a system, you add interactions perturbatively, you can modify Fouquet's Fermi golden rule and just take into account that energy, this is not just initial minus final, but you can add or subtract integer multiples of your driving energy quantum h bar omega. And so this complicates engineering of many body systems, because as you can imagine, if you periodically drive your system, eventually it will always heat up to infinite temperature because it absorbs energy from the drive, and then you get some featureless quantum system. But here you can also see a couple of strategies that allow you to find a more stable parameter space. So first of all, you want to have h bar omega large. What you want is to shift these copies very far away. So if there's any way you can increase omega, you should definitely do that. And there are other things you can see that, there are ways to avoid these resonances. In our system, that would be having resonances that form doublons. Like if initially you have singly occupied sites and that form doublons, you want to avoid that as well. And so we have actually compared that to some of our early experiments where this matched quantitatively. And so this allowed us to now scan the parameter regime and create a stable system of many interacting particles, in this case, quasi 1D. So what we have picked is a ladder geometry that you see here. So there are two sides coupled along X, and there's an extended coupling along Y. And it's pierced by a magnetic field of pi over 2. That would be the phase associated with one plaquette. And we have strong Hubbard on-site interactions on the order of 11 J. And this is a rather interesting system because the phase diagram looks what you would expect from a type 2 superconductor. So what happens to the phase that you see in the lab as a function of magnetic field is that as you ramp up or increase the magnetic field, there's a carrier current that develops around the legs or the edges of your system, which expels of course here we don't generate real fields, the magnetic field that is trying to penetrate your ladder system, up to a point where you hit a critical value of the magnetic field, and this carrier current breaks into current vortices. So this phase diagram has been studied in the non-interacting case, and we have now extended this to the interacting case. So here we don't tune the external magnetic field, but the coupling ratio. The physics is the same. You get a transition from a Meissner phase, which has these nice carrier currents, into a vortex phase where this current pattern breaks up into vortices. And here there's an interacting version of this. So the non-interacting one would be the dashed line. The solid line is the theory for the interacting case. So this is an insulating phase, which has these carrier currents around these edges. And this has been realized now in a large system of roughly 50 sites. So these are 25 particles that are now engineered in this interacting ladder with flux in our system. So this is quite exciting, I think, because it for the first time shows you that this technique of engineering gauge fields can actually be extended to the many-body regime. And there is hope to see fractional quantum Hall phases in large systems. Now the question is how good we are doing in extending this to 2 dimensions. And let me also emphasize the challenge, or why we are not there yet. And I will not be able to present this to you in the next few weeks. We have benchmarked the temperature or entropy in our system that we get. And it's low, but it's on the order of this tunnel coupling J between neighboring sites. And the many-body gap for the Laughlin phase, for instance, is 1 order of magnitude lower. So not quite. So we are maybe order 1 away, but so we are getting there, but we are not quite there yet. Okay. Questions? Yeah.
There are a well-defined path to getting colder.
I think so. Unfortunately, it requires rebuilding the machine a little bit, which is a bit annoying, the annoying part. I think key from all the spectroscopy also that we have done is to increase the modulation frequency and decouple energy scales better. And the way we want to do is actually use 2 different internal states, 2 different Zeeman states, and have an actual Raman coupling between them, because then this is about megahertz. So it's 3 orders of magnitude larger than what we have now. And this should be able to suppress many of the resonances, which goes the heating rate goes exponentially down in omega. So I think this would be the best way of getting there. Yeah.
You have a
1/2. Yes. It's essentially hardcore bosons, so we are also avoid doublons, and it's at a filling 1/2.
case energy, I guess.
J?
K over J, right? So case again.
Yeah, so I went a little, so this is a bit like tuning the flux, but not quite. So K over J is actually the coupling ratio. K is between the 2 legs, it's the rung coupling.
Okay, so it's just coupling constants.
Yes, it's just coupling constant. It's a bit similar, like changing the magnetic flux, but it's easier to explain the picture with flux. Yeah. Okay. All right. So now, in the last few minutes, I would like to highlight that there are things that we can do that we don't already know exist in condensed matter. And now we can try to engineer phases that are topological, but genuine out of equilibrium topological phases. So something that you would not just find if you do Hall bar measurements on a solid state system without any additional manipulation. And so originally all this field was motivated by the fact to understand quantum Hall systems, and in particular fractional quantum Hall systems. And what you know is that there's something interesting happening at the edge. So you have a topological invariant that characterizes the Hall plateaus, but there are also chiral topologically protected edge modes at the boundary of the system if you have a transition between 2 distinct topological phases of matter. And there's a direct correspondence between this topological invariant that characterizes the band and the number of edge modes that you have at the boundary of your system. In periodically driven systems, this does not need to be the case. You can engineer a situation where the topological invariant that characterizes the bands, the Chern number, vanishes. It looks trivial, but you still have chiral edge modes in your system, topological edge modes. And the reason is that if you reformulate naively your Bike boundary correspondence, it essentially means that the number of edge modes, which is shown here in red, leaving the band from the top minus the one entering from below, gives you the Chern number of the band in the middle. And in a static system, you have a true lowest energy band. You know what's the ground energy band in your system. In a periodically driven system, that's not the case. There can be, because this point down here is equivalent to the one up here. It's a Floquet-Brillouin zone. So you can have an edge mode that winds around this Floquet-Brillouin zone. So you have 1 minus 1 equal to 0. And essentially means you have one chiral edge mode that extends across your full energy spectrum. And that's quite neat because there are new phases that have been predicted which respond differently to disorder in the system. And really studying this interplay between topology and disorder is also what makes topology interesting in the first place. So it's something that we would like to do, add a controlled amount of disorder to our system. So we realized this model in a periodically driven hexagonal lattice. So it's essentially graphene that we periodically modulate as a function of time. It's a completely different system, but what I want to show you is how we generate topological edge modes and actually use them as a probe for topological phase transitions in the presence of disorder. Okay, so in this case, it's a hexagonal lattice. And the way we populate the edge mode is by using a tweezer, and we populate the edge mode by placing a BC at a topological interface. So we use a digital micromirror device to generate a repulsive potential. This you have seen before. It's a bit like the box. And then we move our BEC to the edge of this inverted bucket, which is forming our topological interface. So we have a topological hexagonal lattice where we can tune the topology, either conventional quantum Hall or this anomalous regime. And this is essentially vacuum. So we block parts of our lattice where the atoms cannot go to. And then there will be a chiral edge mode forming at the interface. Okay, so now you see snapshots of this BEC that we put outside of this inverted bucket. So the dashed line is where we block sites. And then we follow this wave packet as a function of time. And what you see is that it starts to wrap around the outside of this bucket, and it doesn't propagate into the bulk of the system. So these are raw images. I haven't subtracted any of the bulk propagation. The atoms just really wrap around the outside of the cylinder. And if we change the direction of the topology, if we change the chirality of the modulation, this is a subtraction of the two images, you see that it moves in the other way. And this is actually quite fun because we can now play around with the shape of this interface. So we ask questions about how big does this potential step have to be in order for the edge mode to form. We can play around with the shape of this edge mode. We have made like small quantum point contacts and build small interferometers where we smash edge modes into each other. We haven't really done anything else with it because I don't know yet what it is good for. But you can play these games and build little interferometers. And we have also played with the sharpness of the edge. So you can make it smoother and ask questions about what happens to the velocity of the edge mode in this system. And more importantly, we have developed these techniques because they're these anomalous systems that show chiral edge modes, but where the bulk, the Chern number, is vanishing, it's 0. So we really need the edge mode as a tool to probe topological phase transitions. And this is actually quite interesting because now we can add control to this order. We can add a speckle potential to our system and ask what happens to the topology. And here we also make use of mode matching because the shape of the edge mode at an interface has a certain structure associated with it. It's localized in real space, but it also has some phase winding depending on at which quasi-momentum it lives. And so you can play around with the properties of your initial state to have good or bad mode matching of your initial wave packet and the chiral edge mode. So what you see here is that if we prepare very shallow tweezer, which means the wave packet is quite broad, then it has still a very good overlap with the edge mode in this anomalous Fouquet topological regime. But if we go to a Haldane regime, it's very poor. And the reason is because in this case, there are edge mode at k and k prime points. And I need to go into all the details, but the quasi-momentum doesn't match very well. So there's a poor overlap between these states, which I could improve if I wanted to. But I can use now exactly this regime in order to probe the topological phase transition as a function of my modulation parameters between the anomalous topological regime and the conventional Haldane regime. And then I can use this to probe how this phase transition changes as a function of this order. So what you see here is that we use the center of mass distance, so just measuring how far the edge mode propagates as a function of the modulation frequency, which tunes from this anomalous regime into the Haldane regime. So there's nothing in the Haldane, and then an edge mode starts to appear. And now we can use this to map out the phase diagram as a function of this order. So VD is the strength of the speckle potential in order to probe how the phase transition shifts as a function of this order. And we see that the anomalous regime broadens as a function of this order, which was expected theoretically because it has extended chiral edge modes on all quasi-energy states. So it's expected to be more robust as we add this order to the system. Okay, and with this, I would like to stop and just tell you what my group is working on. A quick overview besides this topological systems. So one of the big topics that we are motivated to do is working on lattice gauge theories. I told you that we would like to have more applications for our quantum simulators. And lattice gauge theories appear in many areas of physics or in general. So it extends from high energy physics to strongly correlated electrons in condensed matter to topological quantum computing. And the structure is very similar to what we have in the lab, but now what we need is gauge fields that mediate interactions between matter particles on the links. And we have two projects that are dedicated to work on this. And one of them is with ytterbium atoms. And so let me just finish with a quick overview. So we have one ytterbium fermionic quantum simulation experiment where we have a hybrid lattice tweezer configuration. We load the atoms directly from the mod into the lattice and cool to the ground state in order to have fast repetition rates. I told you about the sampling problem. So we want to have a lot of data that comes out of our experiment. We have clock states available. So we have a large range of possibilities to implement state-dependent mobility, but also we can nicely use it as a quantum simulator for open quantum systems, where we have like coherent qubit control in each one of these pinned atoms in the tweezer, and where the path is given by atoms that can move around across all the sites in the square lattice. So we have access to system and path, which allows us to also study path-mediated interactions and open quantum systems that go beyond the Markov approximation. We have another experiment dedicated to digital quantum computing, where we make use of the nuclear spin 1/2 qubit in ytterbium, where we work towards error correction and feedback. And then we have a new project that is more dedicated to high precision spectroscopy and fundamental physics, where again, ytterbium has very nice properties. It has the standard optical clock transition, which is very well studied and robust, but it also has yet another clock transition that is very sensitive to alpha variation, which can be used for local position invariance tests. Or something that I'm quite excited about these days is to identify protocols where we can generate coherent superposition or entangled states by making use of all these tools and sort of find a way to couple it also to gravitational effects, which has been done already by measuring the gravitational redshift. So that this would be a very nice platform to sort of study this fundamental interplay in a system where you have quantum mechanics and gravity, and then we'll need to see how far we can push it. But I think it's a very nice application also for these neutral atom experiments. Okay, and with this, I would like to thank my people that are working on all these projects, delocalized at the moment between Munich at LMU and Max Planck in Garching. So thank you very much.
Okay, thank you, Monika, for the talk. Questions? Oh, sorry. Yeah.
Thank you so much for this beautiful talk, and the work is beautiful as well. I was wondering about the last part where you were looking at the time evolution of the edge states and you were, if I'm not wrong, looking at the number density.
Yes.
Right?
So,
will it be, or is it possible to look at other observables for these time evolutions as well, like your previous?
So in principle, yes. So this particular experiment where we realized the anomalous Fouquet in a hexagonal optical lattice, it does not quite have these capabilities. It would still need to be extended. There's no fundamental reason why not. In principle, yes, we would not be able to do this right now.
Other questions?
Hi, thank you for the talk. I have a question on a similar topic. One is this circle or the line is one hexagonal unit cell?
No, so yes, so I was a little bit too fast on this one. So I had put it on the slide. So the lattice site, so the lattice constant is 287 nanometers, and the width of this edge is about 2 to 3 lattice sites. So it's smooth end. It's not sharp on the level of one site.
And could you comment on why the edge mode kind of stops at, I don't know, why does it not go full circle?
Yeah.
It's kind of the question that I had.
Yes, yes. So this is due to the finite lifetime of the atoms in the system as we start modulating it. That's one answer. And the other is that because the edge is not infinitely sharp, the dispersion of the edge mode is not perfectly linear. It does start to hybridize with the bulk energy band, so it requires dispersion, so that the wave packet also broadens as a function of time. So the signal to noise is worse as we wait longer.
Thank you.
Thank you for the talk. I had a quick question about the speckle stuff you mentioned. I was curious how you guys are controlling that, because from what my experience has been working with DMDs, speckle is normally like correlated to like the coherence of the light. And so I'm curious if you guys have a way of like manipulating that using that coherence, or if it's a different way of controlling speckle.
Yeah, we just use a diffuser. So
Okay.
we have just a big beam, we have a diffuser, and then we project it into the atomic plane.
Okay, makes sense. Thank you.
Okay, maybe one more question from anyone?
On the last thing you were showing about the alpha variation,
Yeah.
I didn't quite catch it. You have two species or
So-
two clock transitions in one species? I didn't quite
Yes,
catch.
so there are multiple clock transitions. So there's the standard one. So ytterbium has this singlet triplet spectrum, this helium-like. So one is 03P0 is the standard clock transition. And there's another one. So ytterbium has this F shell of electrons that is also needs to be taken into account for all the transitions. And there's an excitation of one of these F shell electrons into a higher lying orbital. So it's a J equal to 2 state. And this one is sensitive, well, is predicted to be very sensitive to alpha variations. So you could, in principle, have a machine that can probe both in the same experiment, with the idea that, you know, all the systematics that need to be taken care of, you have an easier time because the thermal environment is the same, electromagnetic environment is the same, and so
I
that
see.
would be the idea.
Thanks.
Okay, well, thank you everyone for your questions. Let's thank Monika again for the talk.